Good morning, everybody, to our morning session of this last conference day. Our first speaker today will be Professor Lucio Centrone, and he will speak on perspectives in Specht's problem. Please.
Thank you. Thank you very much. Good morning, everybody. And let me thank the organizers for the invitation. Well, I would like to speak about this Specht problem. And let us start with some definitions. Maybe you already saw something about polynomial identities in some previous talks. Okay, we shall denote the field by F, by the letter F, and we shall work with some variety of algebras. We shall denote this variety by the letter C. We also take in consideration a countable infinite set of indeterminates that we shall denote by X, and the free algebra generated by X over F. Simply, you imagine the polynomial in this variable, x1, x2, xn, x what else, with coefficients in the field F. Okay, these are called polynomials. In what follows, we shall adopt this notation. With capital A, we have associative algebras, capital L, Lie algebra, capital J, Jordan. Now, we have the following. If we take any algebra in this variety and we take a polynomial, we say this polynomial is a polynomial identity for the algebra A if it vanishes under all substitution. Okay, all substitution of the previous algebra. What the ideals are? So we collect all the polynomial identities of a given algebra. This guy here is an ideal. It is invariant under all the endomorphisms of the algebra A. That's why it is called the ideal transformation ideal. So the transformation ideal, the T ideal, is simply the set of all polynomial ideal of an algebra. It is an ideal with the condition, not the condition, with some more property. It is invariant under all endomorphisms of the free algebra. Okay, we have a set inside the polynomials, a set of polynomials, and we denote by this guy here the smallest T ideal containing S. This is called the T ideal generated by S. We also have to introduce one more object here, that is the relatively free algebra of A. In few words, it is exactly the rings of polynomials, the algebra of polynomials, quotiented by the T ideal generated by A. The T ideal of A, of polynomial identities of A. Okay, we go further. We have an algebra A inside the class we have fixed at the beginning of the talk, and we consider the class of all algebras in the class C, so that its polynomial identities contain the polynomial identities of A. This is called the variety of algebras generated by A. So we fix an algebra in this class. We consider all the algebras in this class so that their polynomial identities contain the polynomial identities of A. So this is, in few words, the variety generated by A. We have to talk a bit about multilinear polynomials. So in order to draw off what multilinear polynomials are, I sketched 4 important items about. So we take a polynomial inside this free algebra. This is, of course, said to be multilinear if it behaves as a linear function in each of its own variables. Okay. We also have the definition of alternating polynomial. What is an alternating polynomial? We find 2 variables inside the polynomial, we change them, and the polynomial obtained substituting the first one with the second one and vice versa equals minus f. This is an alternating polynomial. The set of multilinear polynomials of degree n will be denoted by this guy here, Pn. It is a vector space over F, and moreover, it is also an Sn module, where Sn is a symmetric group of order n. And we want to relate these multilinear polynomials with some algebras. So we take the algebra, we fix an algebra inside our variety, and we consider this factor space here. So multilinear polynomials factor the multilinear polynomials of that algebra, which are polynomial identities for that algebra. So in few words, roughly speaking, this is simply the set of non-polynomial identities, non-multilinear polynomial identities of the algebra A. We also have to see some, we would like to study this guy. And this PNA as a vector space is a vector space, and we shall denote by CNA its dimension. This is a very important object of study in PI theory. Try to imagine that this PNA grows at most exponentially. It is a theorem by Regev, despite the fact that the polynomial identities, the multilinear polynomial identities of any algebra, they can grow factorially. So this is a very, very important fact. So in PA theory, it's more common to study PNA than the set of multilinear identities. It's much more efficient because it grows exponentially. Specht problem. What Specht problem is? We fix again an algebra inside the variety, and we say that this algebra satisfies the Specht property if given a subvariety of the variety generated by A, its T ideal is finitely generated as a T ideal. Okay, we didn't speak about this, but it is very difficult to find out a finitely generated T ideal as an ideal. But the question is different. The question is finding a finite set of generators of the T ideal as a T ideal. Okay, they are 2 different things. So the Specht property related to an algebra A is simply finding out if any of the subvariety of the variety generated by the fixed algebra is finitely, the T ideal of this subvariety is finitely generated as a T ideal. This is also known as the finite basis property for the subvariety. The Specht problem. I don't know if you're able to see this, but I'll try to The Specht problem is the following. Is it true that given a variety, it satisfies the Specht property? For example, we take an associative algebra. So it is true that any algebra inside any associative algebra satisfies the Specht property. Is it true that given a Lie algebra, it satisfies the Specht property, and so on and so on? So this is the Specht problem. So we start looking at the associative case. It was the first, okay, we shall speak about Kammer's work. This was the first attempt to give a generalization of the Specht problem. Although similar theorems, similar results have been investigated in a group theory environment. So let us see the algebra environment, and let us see the associative case. So until explicitly written, the algebras cited in this section are associative. Also, the field is supposed to be of characteristic 0. This is the result by Kammer. Any associative algebra satisfies the Specht property. What I would like to share with you. What I would like to share with you is part of the proof. Okay, the longest part, maybe not everybody knows this, but this result I've cited some seconds ago was published in a book. So the proof presented by Kammer is a very deep proof from a mathematical point of view. And sometimes it was considered something very hard to be understood. So I would like to share with you some part of the proof, of the original proof of Kammer's work. In my opinion, well, the proof of Kammer starts this way. I would like to show that every associative algebra satisfies the Specht property. So he knows that he could divide the proof into two parts. The first one is related to finite dimensional algebras, the finitely generated algebra. The second one is going beyond finitely generated algebra through an easy trick using the Grassmann algebra. So the most difficult part and the longest part of Kammer's program, Kammer's proof, is devoted to the following: the representability of finitely generated algebras. What is representability of finite generated algebras? Simply, you take a finite generated algebras, is able to prove that its T-ideal, the ideal of polynomial identities of these algebras, coincides with the T-ideal of polynomial identities of a finite dimensional algebra. This is the representability. So this step is the more difficult and the longest part of the proof of Kammer, of Kammer's proof. So let me list all steps. And we start with step 1. For every finite generated algebra W, exists a finite dimensional algebra so that its T-ideal is contained in the T-ideal of W. So this is a fact. This is easy to prove. So if you take any finite generated algebra, of course you have a T-ideal of finite dimensional algebra contained herein. Step 2, this is a very hard mathematical object. Kemmer constructed the Kemmer index of a given T ideal. So you take a T ideal gamma, and its index is a couple, alpha S. The first entry is the maximal integer m, so that it is possible to find out a multilinear polynomial not belonging to the T ideal, alternating on an arbitrarily many sets of variables of size m. So this is, in a few words, a very special polynomial. So this polynomial is a very critical polynomial. I would like to see that the second part may make the things clearer. The second entry S is the maximal integer, so that we can find another multilinear polynomial not belonging to the T ideal, alternating on some sets of variables of dimension size m plus 1. So this is the difference between the first one. This is the problem. The problem is the following: you have a multilinear polynomial alternating on sets of variables of size m, and the other one is alternating on some other sets of variables. Why it will construct these polynomials? These polynomials are so special that if we move one of these variables, you get a polynomial identities. So its problem was efforts were concentrated in finding out this spatial critical polynomial called Kemmer's polynomials that are not polynomial identities for a suitable algebra. So this is the very delicate point of Kemmer's program. Step 3, basic algebras. This is a topic. It is a fashion topic in associative algebra. What they are finite dimensional algebras whose index is d s minus 1, where d is the dimension of the semi-simple part of A, and S is the nilpotency index of the Jacobson radical of the algebra. That's why I used characteristic zero, a characteristic zero field. Finitely generated algebra, we take a finitely generated algebra W, then it proved that there exists a finite dimensional algebra B having the same index of W. Moreover, they share the same set of Kemmer's polynomials. So that those polynomials that are not polynomial identities, but they are very critical. Step 5 is the proof of Phoenix property. You take G being any Kemmer's polynomial of T ideals, you take F. You see here, this is the first time we meet this symbol. Of course I already explained what it is. It is an F. This polynomial F belongs to the T ideal generated by this chosen G, so that F does not belong to our T ideals gamma. And the Phoenix property is the following: if F is not the Kemmer's polynomial of gamma, there exists another polynomial inside the T ideal generated by F, so that F line, this polynomials F we found here, is a Kemmer polynomials for gamma. In order to prove this, Kemmer used step 3 and step 4. The last 2 steps are the following: construction of a representable algebra, as I told you at the beginning. Step 7 is the final conclusion. You take S to be the T ideal generated by all Cameras polynomials of gamma. You take gamma line being the sum of these two, of gamma and the T ideal S. This simply means that we can use induction here because the index of gamma line is strictly less than the index of gamma. So for this gamma line here, we have by induction, there is a finite dimensional algebra A line, so that gamma line, that is a T ideal, is exactly the T ideal polynomial identity of A line. It is also possible to prove that every element of S does not lie in the T ideal of B gamma, and any non-identity of F line of gamma belonging to S gives out a Cameras polynomial for the algebra B gamma. This simply gives us that F line is not in this T ideal, and this forces our gamma being the T ideal of A line plus B gamma. So this is finite dimensional, this is finite dimensional, this is finite dimension, the sum is finite dimensional. So we found out that our T ideal gamma is the T ideal of a finite dimensional algebra. So this is in few words, in few steps, Cameras program. So a preamble. Associative case, I would like to explain the title of this slide: Graded algebras and module algebras. Of course, in PA theory, one of the main problem is finding out qualitatively the generators of a T ideal. This is not possible. I mean, this is a very big deal. It is a big deal because try to imagine, it is only known the T ideal of identities of the algebra of 2 by 2 matrices. 3 by 3 matrices sounds being something very, very difficult to find out. Maybe the problem has not an answer. I don't know. So what mathematicians do? We try to weaken the hypothesis, and this is provided by graded algebras. So we have the same structures of polynomial identities for graded polynomial identities. These are polynomials with some variables. These variables have the differences that they have in the upper right corner some index, and this index simply means some element of a group. So in few words, you have an X, you have some name of this X, and one more name that is an element of the group. This means that when you will substitute elements inside this object, you can only substitute the element of a given homogeneous component of a G grading of this algebra. So this is simply a preamble in order to introduce you graded algebras and graded polynomial identities. So they are simply polynomials in this set of variables, but you can substitute not everybody, not everything, but simply the homogeneous component of the algebra you already choose. So let us see what is the situation, Specht problem in the graded algebra in associative case, but a great part. 2011, Irina Sviridova proved that if you take a finite abelian group and a G-graded algebra satisfying an ordinary polynomial identity, then A satisfies the Specht property. 2010, so 1 year, they had some problems in date of publication, but the two results are independent. And one is the generalization of the other. 2010, Al-Jadef and Kanel-Belov proved that given a G-graded algebra A, where G is any finite group satisfying polynomial identity, then A satisfies the Specht property. So These are the two results. 2016, we have a new version of Specht problem for algebras with an action of a Hopf algebra. There are some spatial algebra called H-module algebra, and H is finite dimension and semi-simple. So the theorem by Karasik is the following. You take an H-module algebra satisfying an ordered polynomial identity. H is a finite dimension semi-simple Hopf algebra. Then A satisfies the Specht property. So I simply list these results. Until now, I simply listed these results, but I would like to highlight what are the differences between one result and the other. For example, the Al-Jadef and Kanel-Belov version is the following. They have alternation of G-graded variables. So you have two variables. They are labeled with elements of the group. So if you take this one and this one, and you change the order of the variables now as a grading given by the product of the two elements of the group. But in any group, if you change if you take any group, the group is not always abelian. So you have this polynomial belonging to different homogeneous component. So this fact led them to consider alternating sets which are homogeneous, the variables corresponding to the same component. So this is a difficult part. So they found out some polynomials invariant under some alternation of variables. So this is the main difference between the Al-Jadef and Kanel-Belov version against the Kemmer and Irina Sviridova version. The last one I mentioned was the work by Karasik about H-module algebra. What is the difference between this work and the Al-Jadef and Kanel-Belov one? The step 3 of our Kemmer's program, well, it relies exactly on the knowledge of the decomposition of the algebra of the initial algebra in a semi-simple and radical part. This is extremely important. This was done for H-module algebras by Gordienko in 2013. And Karasik was able to adapt this classification to the construction of H-module algebra, basic H-module algebras. I would like to highlight once again that basic H-module algebras are a trendy argument in associative algebras. They are unknown. Their structure is unknown. Now we go further and we talk about superalgebras with superinvolution. These objects were used massively by Zalmanov in one of his main works. And what is a superalgebra with a superinvolution? Is a Z2 graded algebra with a map which behaves more or less like an involution, but it has a difference. Well, star of A is A, and star of AB is -1 to the degree of A times the degree of B, B star, A star. But A and B must be homogeneous. A superalgebra with a superinvolution cannot be considered as a Hopf algebra. So if we want to study the superalgebra with superinvolution case of a Specht problem, we cannot relate to the Karasik or Al-Jadef and Kanel-Belov work. But we have this result. Given a finitely generated superalgebra with superinvolution, satisfying an ordinary polynomial identity, then A satisfies the Specht property. This is done by my PhD student, Antonio Iopolo, and by myself. What is the difference here? Description of the simple component of a finite dimensional superalgebra. This is different than the other cases. And the construction of Kramers polynomials has to follow a map, the superinvolution, a gradient, as in the case of Sviridova, and they have to mix them. The construction of the Kramers polynomials was completely different than all the other cases. Okay, I also pointed out that the general case is still open. We have counterexample to the Specht. We are still in an associative environment. Ground field of characteristic not zero, showed by Kanelbelov, Grishin, and Shigolev. Okay, here I simply wrote here the very interesting fact that they published 3 different counterexamples in the same journal, in the same issue of the same journal of the same year. It was something very, very, very interesting. We would like to introduce the finite basis property for sets. This was something studied by Erdős and Rado. Some other authors studied the finite basis property for sets, also known as the theory of well quasi-ordering. And I would like to share with you these definitions. So we take binary relation on a set A. Why I'm going to introduce this object? Because of course we will use the finite basis property for sets in order to give an answer to other cases of the Specht problem. We have a binary relation on a set A. We say this is quasi ordered if this relation is reflexive, transitive. Please notice that every partial order is a quasi-order, but not the contrary. For example, this is a very we will use this quasi-order here. We say that f is less than or equal to g if and only if g is inside the T ideal generated by f. This is a quasi-order, but in general, this is not a partial order. Partial order means that f less than g, g less than f means f equals g. This is false because g can belong to the T ideal generated by f, f can belong to the T ideal generated by g, but f and g can be totally different. We take a subset of a quasi-ordered set A. Its closure is defined as of course as the all B inside all A in A, so that there exists a B less than or equal to A. Closed subset is simply a subset coinciding with its closure. So a quasi-ordered set A has a finite basis property if every closed subset of A is the closure of a finite set. This is simply a remark here that every well-ordered set has the finite basis property, and with its standard ordering as a finite basis property. We have this equivalence theorem. Every closed subset of A is the closure of a finite subset. If B is any subset of A, there exists a finite subset B0 of B, so that B is intertwining B0 and its closure. Every infinite sequence of elements of A has an infinite ascending subsequence. And there we also have the fourth item here. This is an equivalence theorem for closed subset. Okay, what we have here, we take an algebra A. We consider the set of all finite subsets of A. And we define here for this P and Q inside the set of finite subsets of A, this relation saying that P is less than or equal to Q if you have an increasing map from P to Q. We have here some explanation. If A is, for example, the set of natural number, we can define a quasi-order set on Sn in this way. We can compare two sequences here with this less than or equal to, if and only if we have another subsequence of a line so that they are mutually comparable. Resolved by Ernst and Arado. If A has a finite basis property, then so as the set SA. Okay, let us go back to Specht problem. I will show you how these two theories go into one into the other, how they influence each other. And we go back to polynomial identities. So we recall the order, the quasi-order established at the beginning as an example. F is less than or equal to G if and only if G belongs to the T ideal generated by F. Given a T ideal of a T ideal inside the free algebra, the quasi-order is inherited by the relatively free algebra. Okay, so now we try to establish a quasi-order here, saying that F and G are one less than or equal to the other, if and only if G belongs to the T ideal generated by I, of course, and F. It's exactly the same thing. We say that G is a consequence of F modulo I, in this case, or that G is a consequence of F. In this case, as I told you, this is not a well-ordered, because if F is less than or equal to G, or G equal less than or equal to F, we don't have an equality, but we write this equivalence. F is equivalent to G. Observation: if B is a set here, its closure is inside the T ideal generated by B. Of course, modulo I, because we are working in this relatively free algebra, and we have that the T ideal generated by closure is the T ideal generated by B modulo I, of course. Now we fix a variety of algebra so that its T ideal is finitely generated. And we give a strategy to give a positive answer to the Specht problem. The steps are simply two: finding a set of polynomials, not it could be also an infinite set, so that for some of its subsets, its T ideal coincides with I. Second step, show that the set we found before in step 1 satisfies the finite basis property for sets. What happens? Supposing that there exists a set B satisfying 1 and 2, and I is the T ideal generated, a T ideal of R. Now we can find a B line inside B so that I is the T ideal generated by B line. Since now this guy satisfies the this property, we have the positive solution by the equivalence theorem we gave before. So we have that I is the T ideal generated by B line, which is the T ideal generated by the closure of B0. It was the second step of the equivalence relation, which is exactly the T ideal generated by B0. Okay, so B0 is finite, and then we have the positive solution for the Specht property. This is what happens in this case. That's why it's good to use the finite basis property for sets in this case. If we have a field of characteristic 0 and this guy is finite generated, the natural set satisfying step 1 of the previous 2 steps is the set of highest weight vectors generating irreducible modules, of course non-zero one. If we have a concrete list of highest weight vectors, now we have to show that this list satisfies the finite basis property. How we can do this? We have a strategy. The strategy is close to the one used in Buchberger algorithm or Diamond's lemma for Grover basis. Okay, if we have if the multiplicity is 1 in the decomposition of irreducible modules, it's sufficient to show the 2 steps in order to prove the Specht property. If the multiplicity is no more 1, we have to reduce something. We have to reduce something through this algorithm. I told you it is close to the algorithm used by the Buchberger algorithm. The first step is the following. So we have to order the element that generates the highest weight vectors, and we have to select one, the leading term. Second step, define partial quasi-order on all this guy and prove that the set of these highest weight vectors satisfies the finite basis property with respect to the previous quasi-order. The step 3 is a rewriting step. I mean, if you take 2 highest weight vectors with 2 linear terms, then you have to find out an highest weight vector here, satisfying the condition here. This is simply finding out something. You have a linear combination of 2. You would like to write them as a linear combination of smaller one. So this is step 4. Step 4 recalls what I told you right now. And maybe it's too technical to show you. Maybe it's technical and annoying. And we go to the non-associative case. Okay, at this moment, the Specht property can be proved for many classes of non-associative algebra. It was proved by for finite dimensional Lie algebras over field of characteristic 0, but it's simply okay. We have a more general theorem. The more general theorem says that the Specht problem is solved positively for Lie algebra satisfying a Capelli identity. It also proved for finite dimensional Jordan algebras on field of characteristic 0 by Weiss and Selmanov, and for bicommutative algebras over any field by Drensky and Zakayev. They also, Benediktovich and Zaleski, proved the following generalization of the result by Ilyakov. if we take Lie algebra over a field of characteristics 0, it satisfies the Specht property if its codimension sequence is polynomially bounded. I told you the codimension sequence is exactly the dimension of the known identity, non-multilinear identity of degree n. I told you at the beginning. General case for Lie algebra sounds to be another big deal. We have a counterexample in case of positive characteristic. In the Lie case, see the von Lie in characteristic 2, von Lie result in characteristic 2, and Dransky for any characteristic. To be true, Dransky showed infinite examples of a counterexample to the Specht problem. More counterexample in non-associative case, Gianbruno, Valenti, Mishenko, Zaitsev, they construct a variety of non-associative algebras, not satisfying Specht property, with a very slow growth of a codimension sequence. Also, this example is very interesting because the codimension grows as n to the 3 plus alpha, where alpha is a real number, strictly less than 1. Also, we have interesting example of non-Spectian variety obtained very many years ago in the 70s by Dransky. And in this case, this is a very interesting case because you give an example of an anti-commutative algebra, which variety has a quadratic growth and not finite based, of course. In the case of Jordan algebra, I told you we have the partial answer given by Weiss and Zalmanov for the general case, but they use a sophisticated, they use massively Jordan pairs, identity of Jordan pairs, and so on. In the Jordan case, we don't have answer for weaker cases. I mean, graded in the graded case, we don't have any result except the result I will show you in a while. Here I'm writing that we don't know yet whether the answer is positive or negative in the infinitely generated case, in the case of Jordan algebras. And also in the case of algebra endowed with some other structures, for example, groups or some other structures. Okay, positive cases with additional structures. Using the method of Specht property for quasi-ordered sets, it was possible to prove the Specht property in the following cases. The first ones who introduced this theory for investigating the Specht property in non-associative case were Gianbruno and Manuela da Silva Souza, 2x2 Lie algebra 2x2 SL2 algebra without with a trivial trace, endowed with any grading, with any group. Soon after, Dinitz and Souza used a similar method to show the Specht property for Jordan algebra of a bilinear form with a Z2 grading. And this result by myself, Fabrizio Martino, and Manuela Souza again about the Jordan algebra 2x2 upper triangular matrices with any grading over any group. Now, these are the well-known cases, and what the literature about Specht problem gives is more or less a very extensive literature about the results in the Specht problem. But I would like to talk you in the final part of my talk about new frontiers and what it is left to be studied, a lot of cases. So what happens with algebras that are not pi satisfying the Specht property, because in all the above mentioned theorems, the one by Irina Sviridova, the one by Al-Jadef and Kanelbelov, the one by Karasik, the one by myself and Ioppolo and Alejandro Serna, every algebra has to satisfy a pi, an ordinary pi, in order to satisfy the Specht property. What I mean here is studying algebras satisfying graded, maybe graded polynomial identities, but they are not pi in an ordinary sense, and study if it's the ideal satisfied, graded the ideal satisfies the Specht property. Of course, this is in an associative case, but of course we can study it in a Lie or Jordan setting. What about general infinite fields? Well, most of the cases here, the most part of the cases is referred to fields, characteristic zero fields. What about infinite fields? What about finite fields? Hilbert series. We in a paper of 1990, maybe it was in 90s, Kanelbelov used the representability of a given algebra of the representability of the relatively free algebra in order to deduce the rationality of the Hilbert series of this relatively free algebra. And it also gives him the possibility to study to show that the relatively free algebra of a pi algebra has a finite and integer Gelfand-Kirillov dimension. The question is, under what conditions the two properties are equivalent? And this last one is about formal languages. How do Specht property and regular languages are related? Okay, what is a formal language? You can think to simply a set of words. Some set of words is a formal language. Now, in Chomsky hierarchy, we have three steps of formal languages. We have four steps. The step 0, Turing machine, step 1, step 2, step 3. Step 3 are regular languages. Our grammatic, our vocabulary, our grammatic is a regular language. So in the language of formal language, what I mean here, Specht property and regular languages. We can study, for example, relatively free algebra. I mean, non-identities of a given algebra. Is this a regular language in a certain sense? This is a very interesting question, and it seems that every cases studied until now, I mean, every case of a relatively free algebra carrying on the property of being a regular language has the Specht property. So the question is, the converse is also true. Does the Specht property influence in a structural way the regular language of a relatively free algebra? This is my third purpose of a frontier in the study of Specht properties. And I'm done. Thank you very much.
Thank you very much for very interesting talk. In fact, it seems there are many open horizons in this theory. Thank you. Are there any questions? or comments? In fact, I have a quick question. Assume codimension sequence is polynomially bounded. You have mentioned a number of results saying that if this is so, then Specht property is true. For example, there was a result about Lie algebras in this flavor. So my question is, how is it possible to extend this result, for example, to Leibniz algebras?
This is a very interesting question. This is a very interesting question. This is a very interesting question. This is my feeling. My feeling is yes.
Mm-hmm.
My feeling is yes, but I tried to do some computation. You see, I can feel a gap between my feeling and my and what works, what the computation gives me out. So, in my opinion, the answer should be yes, but I've not worked seriously at the problem. Mm-hmm. Thank you for this question. This is interesting.
Yeah, it could be interesting, in fact, to see where are the horizons here. Any further questions or remarks?
Any question? So, in the sense of the theorem about Specht property on Lie algebra, is the Lie algebra you told is infinite dimensional or infinite dimensional or both?
I'm sorry, I've not understood the question. You told me about the Specht problem about Lie algebra.
Yes, yes. You mentioned in the middle of our talk as Lie algebra verifies the Specht property on some special situation.
Yeah.
So my question is it Lie algebra of finite dimension or infinite dimension?
Finite dimension. If for finite dimensional algebras, the Specht property is solved positively. So if you take a finitely dimensional algebra, you take it's the ideal, it is finitely generated. If you take an infinite dimensional Lie algebra, you can prove the Specht property, but this Lie algebra has to satisfy a Capelli polynomial. Capelli polynomial is a very special polynomial. You can find it, Capelli polynomial. Capelli. But we also have, this is related to the question of Alexander, the previous question. If you take a Lie algebra having a polynomially bounded sequence of codimension, this Lie algebra can be infinite dimensional, but if it satisfies this property, then it satisfies the Specht property. So it could be also infinite dimension, but it has to satisfy some spatial properties. Okay.
Okay. Thank you for
the field has to be of characteristic 0.
Okay. Thank you for the good talk.
Thank you.
Any further questions? Seems to be this is not the case. So let us thank Lucio Centrone once more.